Hello everyone, my name is Anshumali Karmi and welcome to my tutorial video on chaining and probing. Not the kind that aliens do, but the ones in hashing. Now, what is hashing? Hashing is a process of converting input data into a fixed size string of characters, which typically represents the data in a simplified or compressed form. Hashing is used in various applications like data storage, cryptography, and error checking. Its primary goal is to facilitate quick data access using a hash function to map keys to indices in an array, allowing for fast data insertion, deletion, and retrieval. Hash tables provide O of 1 average time complexity for search, insert, and delete operations, making them highly efficient compared to other data structures like arrays or linked lists. Now, an example of hash table is something we've probably used in Python called a dictionary. So this is usually called a dictionary, and you can store values like key and value pairs in dictionaries, and they're very efficient as well. A more archaic example of a dictionary is an actual dictionary. So let's take an example for surprise. When you're looking for the word surprise in the dictionary, you don't go and check SA or AB, CD. You go straight to SU and then you find your word, which is surprise. Now, let's take a look at chaining, or more specifically, linear chaining. Linear chaining is a collision resolution method in hash tables where each index in the hash table points to a linked list. Now, you may wonder why you need that. Well, let's take a look at the example for our dictionary. So even in a normal dictionary, the letter S, for example, there's like hundreds of thousands of words that start with S, and they can't all be the only one. So that's where chaining comes in, where we kind of chain them each one to another just back and forth based on the order that they came in, or alphabetical in case of the old dictionaries. But yeah, when a collision occurs, the new entry is appended to the linked list at the corresponding index. Each bucket in the hash table points to a linked list that contains all entries mapping to the index. It is very simple to implement, and there's no need to find an alternative slot, and it can dynamically handle an unlimited number of collisions at the cost of additional memory for linked lists. While the average time complexity remains order of 1 for insertions and lookups, performance can degrade to ON in the worst case if many elements hash to the same index. Now let's take a look at example here where there's 5 rooms and there's 5 students who've entered the room and need to be assigned. When we are using hashing, we need something called a hash function. A very common hash function is key mod the buckets or the rooms in this case. So as an example oh, my bad. For example, in this case, the one we have is 10, and when we do 10 mod 5, which is the number of rooms we have, we get 0. So the student would be placed in room number 0. Now let's go through this example here. So as we said, so 10 goes into 0. Now what happens is it goes into the 0 memory, and then it adds a pointer there, and which points to another node, and that's where 10 is stored. So this is where the actual 10 is stored. Next, 13. So 13 mod 5 is going to be 3. So the remainder is going to be 3. So similarly, there is going to be a pointer here that goes and points to 13. So you can see it works really nicely if all of the numbers are in different order. or the mod values are different, which is the reason why we normally use a prime number for the mod value, so that there's only two options, or there is a higher chance of remainders, or like different remainders. So 24 is going to be 4, so 24 mod 5 is going to be 4. And yeah, as you can see, it works really nice if it gets distributed evenly. But if we get like 4 numbers that are all remain all having remainders of 4, it starts to become a chain and it turns into a basically a linked list at that point. And yeah, next up is going to be 33. And yeah, we run into this issue now. So 33 mod 5 is also 3, but we can see that there is already 13 in 3. So when it comes to chaining, we just simply add another pointer from 13 to 33. And just like that, we can basically add an infinite number of linked lists, making it so that this table will basically never be full, no matter the number of students that come in. It can all be handled with these 5 numbers. However, as you can see, number 1 and number 2 are empty, which wouldn't be the ideal case, as we want the students to be distributed in the rooms itself rather than having the linked list be created. So that's when probing comes to play. Probing is a collision resolution method, so it's different from the normal chaining that we just took a look at. As in this, upon a collision, the algorithm searches for the next available slot in the table using a systematic probing sequence. Generally, linear probing is the more common one and is the ones that are going to be asked in the quiz. So there's the other two one as well, so quadratic and double. But linear probing is when a collision occurs, the algorithm just checks the next slot in the array and continuously linearly until like an empty slot is found. So it is very simple and it works quite well, but there are a few other ones as well, such as quadratic functions or quadratic probing, which use the quadratic functions to find the next slot, reducing primary clustering but potentially causing even secondary clustering. There is also something called a double hashing, which uses a second hash function to determine the step size for probing, which provides better distribution and reduces clustering. And the efficiency of probing is that it offers order of 1 average time complexity for insertions and lookups, similar to other collision resolution techniques, but can degrade to ON in the worst case as well. Probing keeps all elements within the hash table's array, providing additional memory overhead required, or avoiding it, memory overhead required by linked lists using chaining methods, as we saw. Now, taking a look at the same example, when it comes to probing, let's see, 10 goes in the same direction. So instead of having a linked list, it just places it in that slot itself, because in probing, it can't occupy more than one place at a time. So each key will have one memory slot. 13 is going to be here as usual, and 24 is going to be here. 33 is now going to be here. So it was supposed to be here, but then it checks the next one. So the next one is 24. So, or like the next one is slot number 4. This is full as well. So now it goes back up to check slot number 0. And you can see that slot number 0 is also full. And then it finally goes and checks slot number 1. This one is empty, so it plops it over here. Now 5 or 15 is also divided by, or 15 mod 5 is also 0, and it checks 0, or slot number 0, sees that something's there, goes to the next one. Slot number 1 checks if it's empty. It is not. And then it goes and checks the next one, which is 2, and it's empty, so it just slots it in there. So as you can see, it has nicely managed to place all the students in the designated rooms. There is no need or hassle for any extra linked list memory or any other kinds of overhead, making it very efficient. And that is all for this video. I will be back with week 11 content soon. So look out for that, and thank you for watching. Bye-bye.